So I'm Matej Hoffman. I'm from the Czech Technical University in Prague. And so the talk that I prepared for today is more really like to start a discussion maybe in the panel afterwards. So this is not like that I will be presenting my work, but it's the topic is basically that I guess many of us have been seeing around that this embodied AI is recently becoming a buzzword, not only for us, but also for other communities like machine learning, deep learning. And what I want to basically briefly sketch in this talk is, whether these communities mean the same thing and what are kind of the, misconceptions and, what would be maybe a productive way forward. So just to give you the context, so I, as many, from this crowd, I originate from the lab of Rolf Pfeiffer. This is the photo from 2012, so that's kind of like one year before I left and before this was kind of the last years of the lab, and you may recognize some faces that are also with us today. So as here I don't need to preach to the choir. The one of the key premises here is that behavior is not in the brain, even though if you, for example, open this Bible of neuroscience, which starts by saying all behavior is a result of brain function. So that's not what we think. It is in the interaction. This is the schematics that has already been presented during this conference, how the body, the morphology, how there is mechanical feedback loops, how there is also this information self-structuring. So the brain, by issuing the motor commands that go through the body and then come back through the sensory systems with the particular morphology, there is a specific information structure that is induced by all these components. And I think that is very important. Of course, morphological computation is another way of looking at the same thing. I have my reservations in calling these things how morphology helps control or perception computation. That's what we articulated in this article with Vincent Miller. But in any case, the key influence of morphology for control and for perception is not debated. And there might be morphological computation proper, where the body, in my view, is really computing, like this physical reservoir computing. So yeah, we know all that. Now, there is really, if you now search for embodied AI, you start seeing it in communities that previously didn't really address these topics. So for example, there is a series of workshops at CVPR, which is this Computer Vision Pattern Recognition Conference, where they had already in subsequent years a series of workshops that they called Embodied AI workshops. The theme of IROS, which is a robotics conference this year, was Embodied AI for Symbiotic Society. There's also people that do reinforcement learning, for example, Serge Levin. So he recently gave a talk that was titled From Reinforcement Learning to Embodied Learning. So I think it's important for us to realize, what people mean when they say embodied AI or embodied learning, and to find bridges between these communities to make the most effective way forward. So that series of workshops at CVPR, they have a paper on arXiv that basically summarizes what this community is doing. The tasks that they deal with are tasks like rearrangement, visual navigation, vision and language, audio-visual navigation, sim-to-real transfer, and what they do is centered around a set of challenges, which are typically simulated environments where you can do these kind of tasks. So what is this embodied AI here? So you see these examples of the tasks. Here they contrast passive AI and embodied AI, where embodied would be, you have a simulated scene, like a house like a household where you need to close the drawer. So you need to move the simulated robot somewhere and open or close the drawer, for example. And these are examples from the other data sets and challenges that they have. So you see that it's a lot about navigation. It's typically like mobile robots in simulated environments doing some not very, let's say, dexterous manipulation tasks, but some rather high level tasks. They employ different architectures, so not only like end-to-end deep learning architectures, but also modular architectures, which is more like the sort of classical divide and conquer approach. Here is a summary of some results they had. So you see that the modular, as the tasks become more complex, that they score better. So it's a kind of leaderboard here. And now this is my kind of take coming from the let's say embodied AI as within this crowd community. So they often equate embodied AI with sim-to-real transfer, and also with multimodal input. So as soon as you have input from more than a single modality, like as soon as you have vision and audio, for example, it's more embodied in their as they see it. Now, in my view, these tasks are still very weakly embodied and highly abstracted, and the interactive actions are not central to the approach, whereas they are central for what we take for embodiment. So here is the list of the challenges they have, and you see that like the first half of these simulated environments of these challenges, they do not feature these interactive actions. So basically, it's like somebody driving a vehicle around, collecting images and maybe other modalities, and that becomes then the data set from which you learn. So you're not, you cannot basically learn on the run or on policy. So I think this is a major limitation of why of the embodiment level in this sense. Okay. So Serge Levin is one, one representative of doing embodied reinforcement learning. So in this talk that he gave recently, that is available online, he talks about offline reinforcement learning for embodied learning and how to make that effective. One of the options is pre-training and online fine-tuning. So what these communities would like to have are big data sets that allow for that. So they would like to generalize over tasks, over scenes, possibly even over robots. So which I think is a very ambitious goal. So we will talk about it a little bit later. You may have seen these videos where different robot arms, like a lot of robot arms, are trying to grasp something, or in this case, they are closing doors. In this particular scenario, there had to be a human that was then closing the door. No, they were opening doors, and somebody had to close the door so that they can try again. So that, of course, is not very efficient. So you can automate it in some ways. One way of doing that is learning different tasks simultaneously, such that the robot can basically reset the world himself. So, and as we know, in all these cases, the real world data is expensive. Yeah, so you need to basically bridge between different data sets. I think that's fine. Of course, this also relates to the talk of Jan Peters today, but I had very little time to sort of incorporate it. If Jan is still with us, then he can certainly speak to this. So this offline reinforcement learning, that's the summary from Serge Levin, provides a tool to reuse data in robotics. You can do that multitask learning to some extent, and yeah, this pre-training and online fine-tuning seems to be a good combination, where you have this. So this pre-training is on a data set where you cannot do interactive learning, but then you basically fine-tune it online. Now, what are the limits of this generalization? So, of course, we want to generalize across tasks and environments. The question is whether we can generalize across bodies. And so, for example, this seminal work by DeepMind, the Gato, seems to claim that you can do that. Now, the question is how much can a giraffe brain? So that this is making a caricature a little bit. profit from a crocodile's brain. So they seem to believe that that you can really do it as long as everything is big enough. But I think that you can do it only in a very weakly embodied task. So as soon as the body, the morphology plays an important role, which is what we understand by embodiment, then I don't think this can ever succeed. So that's something maybe for the panel discussion. So in summary, embodied AI within deep learning. So they give basically these deep learning architectures the body and close the loop with some reservations. The embodiment is, in my view, very weak. What is not exploited is morphology for control and for perception, and this information self-structuring, which you only can get through the body and by actively issuing your actions in the environment. So it's kind of these tasks as opposed to these tasks, we have all these examples that we all know, like the passive dynamic walker or this coffee back gripper gecko, and all this morphology of the retina of an eye, of an insect eye, and etc. The compound insect eye. Okay, so now the open question is: can embodied AI under deep learning be more profoundly embodied? So there are different opinion papers that were published recently. Fumia was looking into for example, how to match the timescales, which is certainly important. We had a contribution by Giacomo Indiveri here. So neuromorphic intelligence can certainly be something. Lessons from infant learning. This is another perspective paper that just came out. And finally, possibly the most straightforward way how to really get embodiment into these end-to-end approaches and the deep learning approaches are these differentiable physics simulators. So where they can differentiate also the body and its interaction with the environment, and hence they can basically backpropagate through the whole thing, including the body, and then the body, by doing that, becomes as important as anything else, as the controller. So that's my take, and I'm happy to discuss during the